Hey there, and welcome. Have you ever just stopped and wondered about the magic that happens when you search for a file or when your favorite app pulls up a contact in a fraction of a second? It feels instantaneous, right? But it's not magic at all. It's actually the hidden genius of something called data structures. So let's peel back the curtain and see exactly how software pulls off these incredible feats of speed. I mean, really think about that for a second. You ask your phone for the best way to get across town, and out of, well, practically infinite possibilities, it gives you the optimal one almost immediately. It's not just trying every single road, right? That would literally take forever. The secret sauce, the real trick, is all in how that data, the map itself, is organized to make searching not just fast, but astonishingly fast. All right, so where do we even begin? Let's start with the most basic problem you can imagine, finding one specific thing. If I give you a username, how does a system find your account info in the blink of an eye? Well, for this, computer scientists came up with this really clever trick called hashing. And this slide has the perfect analogy to get our heads around this. Okay, so on the left, we've got something called direct addressing. Picture a code check room, but it's massive. It has a million hooks, one for every possible ticket number. It's fast, sure, but you'd waste a colossal amount of space for hooks you never use. Now look at the right, that's a hash table. This is like having a super smart attendant. You hand them your huge ticket number, they do some quick mental math, a hash function, and they point you to hook number 57. See what's happening? We're mapping a giant universe of keys into a tiny, manageable space. That right there, that's the aha moment of hashing. But wait, there's a catch. What happens when our super smart attendant's little formula assigns the same hook to two different people? Boom, that's a collision. And, because of a basic math idea called the pigeonhole principle, if you've got more coats than hooks, someone's going to have to share. Collisions are basically guaranteed to happen. And this becomes the central problem that every hashing system has to solve. What do you do when two things want to be in the same place? So how do we deal with this? Well, there are two main strategies. First up is something called separate chaining. This is basically like putting a little rock of extra hooks on each main hook. If there's a collision, you just hang the new coat next to the old one. Pretty simple, right? The other way is called open addressing. This is more like the attendant saying, whoops, hook 57 is taken. Just try hook 58. It keeps everything neat and tidy in one big array. But you can see the problem, right? You can get these big pileups or clusters all bunched together, and getting rid of an item is a pain. The main takeaway here, there's no free lunch. It's always a trade-off. And all this leads us to the one giant glaring weakness of hashing. See, to get that insane speed, the hash function basically throws all your data into a blender. It completely scrambles the original order. So if this was your contacts list, it wouldn't be alphabetical anymore, it'd be a total mess. So yeah, for pure lookups, hashing is the undisputed king. But what happens when you actually need things to be in order? And that's our next big question. What if you want to find your friend Alex, but you also want to be able to just scroll through your address book from A to Z? Well, for that, hashing just won't work. We need something new, a structure that can give us both speed and keep everything sorted.
And for that, we turn to the binary search tree, or BST. It's a really elegant idea, actually. The rule is super simple. Anything smaller than a given spot or node goes to the left. Anything bigger goes to the right. That's it. That one simple rule means the data is always sorted, and finding something is as easy as just walking down the right set of branches.
But like hashing, a basic BST has a huge, fatal flaw. What happens if you feed it data that's already sorted? Like you add the number 1, then 2, then 3, then 4. Well, because each new number is bigger than the last, it always goes to the right. The tree never branches out. It just becomes this long, pathetic, spindly chain. And just like that, our super-fast search has turned into a slow, painful crawl. We're no better off than a simple list. We've lost all our speed. Okay, so how do we fix this? How do we get the best of both worlds? We want the order of a tree, but we need that guaranteed speed. This is where we get into some of the most beautiful and clever ideas in all of computer science. We need a tree that knows how to balance itself. So first up, let's meet the AVL tree, one of the first self-balancing trees ever. You can think of it as a regular BST, but with a superpower. Basically, every single node is constantly monitoring the height of the branches below it, on its left and on its right. And if the difference in height between the two sides ever gets to be more than 1, bam, an alarm bell goes off, and the tree performs this clever little move called a rotation to snap everything back into balance. Now, a rotation is this really elegant, really localized fix. So let's say a node gets a little too heavy on its left side, right? In what's called a right rotation, the left child gets promoted up to become the new parent. The old parent gets demoted and becomes the new parent's right child. You shuffle a few other branches around, and here's the magic part. The sorted order is perfectly preserved. And just like that, the tree is nice and bushy again, which means it's fast to search. But that's not the only trick in the book. There's another kind of tree, called a 2-3-4 tree, that takes a totally different approach. Instead of every node holding just one piece of data, these nodes are more flexible. They can hold 1, 2, or even 3 pieces of data, or keys. And that flexibility is the secret to how it stays perfectly balanced all the time. The key move for a 2-3-4 tree is something called a split. As you're adding new stuff, if a node ever gets totally full, what we call a 4 node, it just splits in half. The middle piece of data gets pushed up to its parent, and the node splits into 2 new smaller nodes. What's so cool about this is that it guarantees that the distance from the top of the tree to any leaf at the bottom is always the exact same. The tree literally never even gets a chance to become unbalanced. It's brilliant. All right, so let's recap. We've got instant lookups with hash tables. We've got fast sorted data with balanced trees. Now let's put it all together. Let's go all the way back to that first question, how in the world does your GPS find the fastest route? This is where we meet the master of the craft, Dijkstra's algorithm. It's a truly powerful and, I think, beautiful strategy for finding your way through a graph. Just think of a map as a graph. You've got cities, which are the nodes, and they're connected by roads, which are the edges. And each road has a distance, or a weight. What Dijkstra's does is find the absolute shortest path from where you are to every other city on that map. So how does it work? Well, the algorithm is what we call greedy. It starts right where you are, and it starts to build out a cloud of places that it knows the shortest path to. And at every single step, it just asks one simple greedy question. Of all the spots I can get to just outside my cloud, which one is the closest? It grabs that closest spot, adds it to the cloud, updates the distances for its neighbors, and then does it all over again. But here's the crucial part, the bit that makes it all possible. To always know which spot is closest, it uses a super efficient data structure called a priority queue. And guess what often powers that priority queue, hiding under the hood? You guessed it, a balanced tree. And this brings us to the payoff. Now, don't get scared by the notation you see here. All this O of E log V stuff is just the formal computer science way of saying that this algorithm is incredibly efficient. It means you can add millions of roads, millions of intersections to your map, and the time it takes to find the best route grows really, really slowly. It's more than efficient enough to spit out that perfect route in the few seconds you're waiting at a red light. So what have we learned here? Well, it seems like every single one of these incredible tools comes with a choice, a trade-off. There's no magic bullet, no single best way to organize data. It always depends on what you're trying to do. And this table here, it really sums up the whole story. If you need pure, unadulterated speed and you couldn't care less about order, the hash table is your go-to. It's basically instant. But if you need that speed and you need to keep things sorted, a balanced tree is the hero of the day. And of course, if you're trying to navigate a giant network, Dijkstra's algorithm, with a speedy priority queue under the hood, is the way to go. So in the end, it really all boils down to that one fundamental choice: speed or order. This is one of the most fundamental trade-offs in all of computer science, and it's happening all around you. Every single app on your phone, every website you visit, its designers made a very deliberate choice on this exact spectrum. Did they optimize for that instant search result, or for a beautifully sorted timeline you can scroll through? Underneath it all, these brilliant, elegant structures are the unsung heroes, silently working to make your digital life possible. So next time you use an app, think about it. What trade-offs are being made for you right now?